In this precept, we plan to cover TST, ternary search trees, Burrows-Wheeler, and LCW. So we start with TSTs. So in this problem, the first problem is about given a TST. You can think of TST as a representation of a symbol table that contains a bunch of strings as keys and a bunch of numbers as values. So for example, that in this case, we have a tree with certain numbers here, and those numbers representing some sort of a string. So we'll take a look at how that works. So one of the things we're going to do is to find out what are the things in this TST in order, in alphabetical order, and then we'll talk about how to insert two new strings into the TST. So in this process, we're going to learn how to, given a TST, how to find the strings in the TST, and then given a new set of strings, how do we insert them into the TST. This problem, we're going to talk about the TST. TST is a way to store strings in a more efficient way, where the characters are at the nodes of the tree. So let's take a look at how we can interpret this TST to find the strings in order. So the main idea of TST is that when a character matches, you go down the middle link. There are three references from each node. If the character is less and did not match, you go this way. If the character is greater and did not match, you go this way. So when you go down the tree, if a character matches, we know that character is going to be part of the thing if you're going down this way. So let's take a look at this. In this case, the character did not match, and that's why we went this way. We found a string called A with the code 7, or the key 7. The key is A and the value is 7. And then if you go down this way, now the character matches, so this means this needs to have a C, and matches because that's why we're going this way, so it needs to have an A, but did not match, and we went this way. So now we're getting the string CAA with the value 5. Now let's do another one. Character match C, match A, match G, match A. So we have this CGAA given to us. Let's look at another one. We have a C match, no match, so G match, so we have CG, and C no match, so this means that we have CGA as the next one. And then we have a C match, G match, C match, A match, so we have CGAA. And then if you go down this branch of the tree, notice that there's a 3 here. C didn't match, so we go here, and T matches, and there's a character there. So therefore, I should have another T here with the code 3. And then if I continue to go down, so we have T and A next. T match, and then no match, and then match here. So we have TCAT. Then we have T's match, no match, so we go to G, and then TGT. And then we have TT, which is 9 here. Okay, so that's how we recover the strings in this character. Now if you're going to insert these two strings into this, so let's see how the insertion works. So we have a C, that's a match. We go down this way. G, the next one, is bigger than A, so we go here. Now G is a match, so we go down this way. Now we have T, which is bigger than C, so we go here, and because there was nothing there, we're going to insert the T. Once you insert the T, it's a match, and then we insert the next T. In this case, we have T, so we go to the right of C. T is a match, and then we go down, and G is bigger, so we go this way. Now G is less than T. It's not a match, so now we have a match here, so we have TG, and then we go down to we are trying to match A, so we go to here. A is less than T, and then we go and insert to the left of it, and that's basically how it works. So the next problem in the handout deals with Burrows-Wheeler transform. To understand the context for this exercise, let's go to the assignment on the Burrows-Wheeler data compression. It's a special data compression algorithm that consists of three algorithmic components. One is called the Burrows-Wheeler transform. That means given a typical English text, you transform that into a text file which sequence of the same character occur near the end of each other many times. And then second step of this process of the compression algorithm is what's called the move to front encoding. So in that case, the given a text file which sequences the same character occur near each other many times, we convert it to a text file which contains characters that appear more frequently than the others. So that leads to a file structure that gives you a way to apply the Huffman compression, which is very friendly to this. Move to encoding gives you a friendly file structure that allows us to perform Huffman compression in a more efficient way. We're going to leave the details to that algorithm for a different video. But for now, we're going to go ahead and solve this problem and really try to understand what Burrows-Wheeler transform means. So let's first learn about just the mechanics of applying the Burrows-Wheeler transform to the string banana. So just to describe this, so given the original string, which we call suffix 0, we'll form suffixes by rotating this around whatever the clockwise or counterclockwise. So we'll get suffixes like we will push this one here and put the B in the back. So we'll get the first suffix to be AN, AB, second one to be NAN, ABA, and the third suffix to be ANA, BAN, and the fourth suffix to be NAB, ANA. Fifth suffix to be ABA, NAN. So I think the next part of this is to sort these suffixes. As we sort the suffixes, you will see that this probably is the first suffix. If you apply something like MSD, you're going to get the first sorted suffix. That's ABANAN. The second suffix would be this one here. So this is first, that's second, or we can call it sorted suffix 0 and sorted suffix 1. And in that case, so we have ANABAN. And the next one is going to be this one here. So that's going to be the suffix number 2, so the suffix number 2, and that's equal to ANANAB. And then we have sort of suffix number 3, which is going to be this one here. So that's going to be B. Oops, let me go back here. So that's going to be BANANA. And then next one's going to be suffix number 4. That's going to be this one here. So that's going to be NABANA. And finally, we have the suffix number 5. That's going to be NANABA. So we got suffixes, then we sorted it to get this particular form. Now the Burrows-Wheeler transform is given by the last column of these characters. So I'm going to write that as NNBAAA, and then the location of the original string in the sorted suffix array. So this was the original string, and that's at location 3. So remarkably, we'll show you how we can recover the actual string given this string here. So in this case, you will notice that the let me rewrite this here. So it's N N B A A A. So you will see that a lot of things appear together, which is very friendly to the next step in the Burrows-Wheeler transform called the move to front encoding. So we'll just wait to learn that step, but next we will continue on to the next part of this this problem. So now let's think about this problem. We have to apply the Burrows-Wheeler inverse transform to find the original string. So this is not the same as the first problem where we just transform a string, but this may be a different string that we have to recover the original string from this given information. What we know is that the string, actual string, is in location 6. So whatever we can recover from here would be the actual string. We also know the last column of the sorted suffixes. So I'm going to write it down, HELWEER. So that's good. The second thing I know, not just this, I know the following. I know the first column. I know the first column because I know they are the sorted, because they are sorted suffixes. These have to be sorted in the first column. So we will have all these first, and then H and L, and then R and W. Now, what we have to do is to really figure out what's in between here to find the original string. That's what our goal is going to be. So in order to come up with a sort of an algorithm to do this, we start with the notion that the first is given to us as 6. The first, let's call that the first. So the next array is that we're trying to figure out if you take the first array and rotate it, where would the W go? It looks like W goes here. So I'm going to draw an arrow here saying the next of 6. The next of 6 is the third sorted suffix. And now we'll take let's look at the next of 3. If you take this and sort it, you're going to get the next of 3 would be this particular thing. That's going to be the sorted suffix with the index 0. And what is next of 0? So this means if you take this and sort it, the next of 0 is going to be this one here, because the E comes to the end. That would be 1. What is next of 1? Next of 1 is if you take E, now notice I've already used the C, that would be this one here. So that would be next of 1 would be 4. What is next of 4? Next of 4 is where the L is. So next of 4 is going to be 2. Next of 4 is going to be 2. What is next of 2? If you take E and rotate it, so the next of 2 is going to be, so next of 2 is, so I'm going to draw like this. Next of 2 is going to be, next of 2 is going to be, let's see, next of 2. Next of 2 is going to be 5. Next of 2 is going to be 5. So that's going to be this relationship here. And then next of 5 is going to be the 6. Next of 5 is the 6. So here's how we solve that next problem. Now, once you have that, it's easy to find out what the characters are. So the first is 6. So we know the first character is W. And if you look at the next of 6, which gives you the character, next of 6 is 3. But what is that character? That character is going to be H here. Okay, that's in the sorted suffixes. So we take that, next of 3. Next of 3 is going to be 0, so that gives us E. And next of 0 is going to give us 1, and that's going to be E. and then next of 1 gives us 4. That's going to be L. And next of 4 gives us 2. That's going to be E. And next of 2 gives us 5. And that's going to be R. So what we did was we figured out what the original string was using the inverse Burrows-Wheeler transform. Finally, let's look at the bonus problem. The bonus problem is about LCW, first the LCW compression, then the LCW decompression. So the idea here is that given an alphabet, let's try to simplify the alphabet to just 2 characters, A and B, and the end of file character, which is 80, and the code table where the next available code is 81. What we need to do is to encode this message AB, BBA, BBA using LCW compression. So how do we do that? First of all, we're going to write the symbols we know, AB. We have 61 and 62. So we can start encoding things. So A is going to be 61. And what I'm going to do is I'm going to show you the try that I'm going to build as I do this. So here's A and here's 61. And then if you look up, you're going to see the symbol AB can be added to the table where the next available code is 81. So I'm going to have AB, which gives you 81. So I'm building essentially a two-way try in this case to demonstrate how I can maintain this the symbol table. So the next character is 62. That's B. And once I have that B, then I can look up and then I get BB, which gives you, so this is B, so I have to start with those 2 characters anyway. So now I have to put the next character, which is BB, that will have the code 82. So BB will be added to the symbol table with the code 82. So now we have BB added. Now there's something nice happening here. Now suddenly we see that what we do is we always find the longest string that can be encoded using the symbols we know. Like for example, now we know that we can replace the BB with the code 82, and then also we can add the new code BBA to the table. So let's call it BBA, which would be the next code available, 83. All right, so and then we have encoded up to here. Now we have AB, which we already have in the code table, so we can say that's 81. And we also add ABB to the AB and the next character ABB to the symbol table. That would be 84. So ABB, let's call it like this, ABB is the character 84. So we have added that, and then we are looking at B, but we don't see BA in our symbol table. So we need to add that, but it's too late to use it. So we're going to just encode B, which is going to be 62, and then add the code BA to the symbol table as 85. So let's add BA to the symbols table as 85. And then we will encode A as 61, which is already there. And then whatever, if you have an end of file here, that would be encoded as 80. So our answer is going to be 61, 62, 82, 81, 62, 61, and the end of file character 80. Okay, so now the decompression part of this LCW algorithm. And as before, we're going to assume that A is 61 and B is 62. While we're building the code table, I'm just going to show you how this is look like in a try. So let's just maintain a try to keep our symbol table. So we have A equals 61, B equals 62. So we're going to start encoding from here. That would be A. I look up and I can add AB to the table. So AB to the table would be 81. That's the next available code. So that's added. And then I look at the 62, which is in the table, which is a B. I look up and I will add 81. 81 is also in the symbol table, so I know 81 is AB. And at that point, I'll have to add BA to the symbol table. So let's add BA to the symbol table. That would be 82. So I've added BA to the symbol table. I've encoded that 81 to be AB, which was in the symbol table. Now, if I look at the symbol table now, I'm in trouble because I see a code that is not in the symbol table yet. So what I need to do is to guess what that code is going to be based on what I know. So it's always the way you think about what will be added to the symbol table is the code you just decoded plus the first character of that code. So let's take that logic first. So the code we just decoded is AB. So, and plus some other character, let's call that X. And that was the symbol that would have added, ABX is the symbol that would have been added to the table if I knew 83. So what I need to do is that I have to get what that symbol is going to be. If you really think about it, that symbol is going to be the previous thing added and one more character. So that would be ABA. So I'm going to claim that this X is really the character A. So this means that ABA should have been added to the symbol table as 83. So I solved the problem here by looking at the previous code that was decoded plus the first character of the previous code. That's the one that would have been added to the table. So this is what you got to deal with when you have a tricky case where you get a code where the code is not in the table. So we took care of that, and so we know now this part is ABA. We also added the ABA to the symbol table. That's good. ABA, it's in the symbol table now as 83. Now we move forward. Now we know what 62 is. 62 is going to be the character B here. Okay, so 62 is character B, and this was encoded, this was encoded, these were encoded. And then finally, at that point, I think we should add the AB to the symbol table. That would have been the next one that's added to the symbol. Actually, AB is in the symbol table here. So let's just take a look at this here. So we found out that the code missing was 83, but we knew that 83 is going to be the previous code that was used, plus some other character, and that character happens to be the first character of the previous code that was used. So that's ABA, and that's added to the symbol table as 83. So the only thing left is 62, which we know is a B, and also we know that the last character 8 is the end of 5. So so that's one of the examples of LCW decoding. You may want to try different problems to practice this a little bit more.